This is the video lesson for Mod 3 Lesson 1, Simplifying Radical Expressions. In this lesson, we're going to look at radical expressions and specifically simplifying square roots. In order to simplify a square root, we need to understand the idea of a perfect square. And the idea of a perfect square is if you have a given square and an area for that square, we can use the square root to find the length of the sides for that square, right? So if I have an area of a square that's 25, the length of each side would be 5. So all four sides are the same, and 5 times 5 is 25. So any value that we can create by squaring a whole number, that's going to create a perfect square. So we're going to use our list of perfect squares with these problems today. And so the first ones here are given for you. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. If I was to do 6 squared, that'd be 36. 7 squared is 49, 8 squared is 64, and so forth. So we can actually complete our perfect square list. And again, that's just by squaring any whole number, and we just want 1 through 12. We can also have perfect squares that are with variables, right? So, for example, x to the second is a perfect square because that's the same as x times x. X to the fourth is a perfect square because that's x to the second times x to the second. X to the sixth is a perfect square because it's x to the third times x to the third. And so what we find is any even exponent is going to end up being a perfect square because it's really, if it's like dividing it by 2 essentially, and then because it gets multiplied by 2. So x to the 8th, x to the 10th, those are all perfect squares because they're even exponents. If I have the square root of 25, it would look like with this radical sign and the 25 underneath that radical. That's the same as saying the square root of 25. And that's really an operation, right? We can evaluate the square root of 25 and we get an answer of 5. So the square root of 25 is equal to 5, and that's because 5 times 5, or 5 squared, gives us this 25. And this is kind of like how we would read this part over here. If I was to do the square root of 36, if I evaluate the square root of 36, that's going to be equal to 6. And the reason is because if I square 6, I will get 36. Same thing with the square root of 100. The square root of 100 is 10. And the reason is because if I do 10 to the second power, I get 100. And really another way, it's really saying what number times itself gives you 100, and that answer would be 10. The square root of 49 would be 7, and again that's saying what number squared gives you 49, and that answer would be 7. So we're just doing the inverse of squaring a number. The same thing applies for even for exponents as well, right? So we can kind of do this a few different ways. It's really, when we're doing the square root of a to the 6th, it's really like dividing it by 2. We really have an imaginary little index of 2 anytime we do a square root. And so it's really like taking the exponent and dividing it by 2 or cutting it in half. So if I have m to the square root of m to the 16th, well, that's the same as really doing 16 divided by 2, and I get m to the 8th. And the reason is because m to the 8th raised to the second, if I did the inverse, that's m to the 16th. The same thing with y to the 10th. It's really like dividing that exponent by 2, right? Because that's a little imaginary 2 that's right there. And so 2 goes into 10 5 times. So that's going to be y to the 5th. And the last one here, if I do the square root of a squared, again, it's like a little imaginary index of 2. That's right there, saying the square root. 2 goes into 2 1 time, so that's a to the 1. And there's no, or you could just write a, and there's no variable under the square root anymore, right? So we just evaluated the square root of a squared. In an expression, the square root of a, we call obviously the square root sign is also called a radical, and the number underneath that is called the radicand, right? And unless there's another number indicated outside, this little number I might even erase. Unless there's a number outside there, we can assume it's a square root. And later we're going to talk about an index and what happens if we do a cube root or a fourth root or a fifth root. When we simplify a perfect square, anytime we simplify a perfect square, we're going to end up with no radical in our answer, right? So I'll even write that at the top. You're going to have no radical in your answer if you're simplifying a perfect square. So if I'm going to do the square root of 4, you can see I have a list of perfect squares over here, right? 4 is actually a perfect square. And what that says is what number times itself gives me 4. 4 is the same as 2 to the second power. So the square root of 4 is 2. If I wanted to check it out, I can see 2 times 2 is 4. Right, so what is going to give me back that 4? So when we evaluate the square root of 4, our answer is just simply 2. For the next one, if I have the square root of 16, that's basically saying what number to the second power would give me 16. And the square root of 16 is the same as 4 to the second. And really my answer would be 4. Even though 4 is a perfect square, I'm not going to take the square root again because I already evaluated the square root. And then the last one, we have a negative out front, the negative square root of 100. 100 is really 10 squared. And anytime I square a square root of square, they're inverses, my answer would just be negative 10. For numbers 6, 7, and 8, kind of skipping a little bit, those have variables, but it's the same exact process. So when we do a to the 6th and b to the 10th, anytime we're doing the square root of a variable, it's like there's a little imaginary 2 out here. That's like our little imaginary, we call it an index. And so that's going to divide those exponents by 2, right? So we're looking for pairs. So if I draw a little radical here, I have a to the 6th, and we would look at how many times does 2 go into 6, right? 6 divided by 2 is 3. And we actually don't have any remainder there. So I would just write a to the 3rd. Same thing with b to the 10th. B to the 10th, 2 goes into 10 5 times. And I don't have any remainder in here, so it's almost like there's a 1 here. So my answer would be a to the 3rd, b to the 5th. So it's really like taking those exponents and just dividing it by 2. And since we have no remainder, there's nothing left in the radical. For number 7, same idea. So we have a variables and we have values here. So I'm doing really the square root of 9 times the square root of a squared. 9 is a perfect square. It's 3 squared. So the square root of 9 is 3. A to the squared is a perfect square. Again, it's just like dividing that exponent by 2. So 2 goes into 2 one time, so 1a gets to come out. And then there's nothing inside the radical anymore. And then finally for the last one, same idea. So we have the square root of 81. The square root of 81, 81 is a perfect square. So we have 9, and then m to the 64. It's like dividing that 64 divided by 2, and we get 32. So you can either write your answer as negative 9m to the 32, or we can write it as, or you could put the multiplication, but usually we like to write it together. For question 1 through 4, what happens if we have something that is not a perfect square? So these ones are, you're going to have a radical will be in the answer. So when we look at the square root of 20, for example, the square root of 20 is not one of these perfect squares here, right? So it's not one of the 1 through 100. So what we have to do is find out, well, what's a factor that 20 has that is one of those perfect squares? So which of these divides into 20? So we can see when we always want to move up the list. It gives us the smallest value possible. And when I look at 20, you know, these are all too big. I'm going to start maybe with 16. So 20 divided by 16 gives me a decimal. 20 is not divisible by 9, but 20 is divisible by 4. So we're going to break up 20 into two factors, where one is 4, that perfect square, and then the other is what multiplies to give us 20. So 20 is 4 times 5. So even though 2 times 10 gives us 20, 1 times 20 gives us 20, we're purposefully picking it so 1 is a perfect square, and specifically the largest perfect square. So if we go ahead and do the square root of 4 times 5, that's the same as using the product rule on the square root of 4 times the square root of 5. I can take the square root of 4. I already know that's 2 squared, or 2. And the square root of 5, I can't go any further. So I'm going to leave my answer. My simplified answer is 2 radical 5. For question number 2, it's the same thing. So 27 is not a perfect square. And so we're going to, again, look at this list. All of these are too big. And I'm going to see which of these is 27 divisible by. So 27 is not divisible by 25. It's not divisible by 16, but it is divisible by 9. So I'm going to rewrite this as 27 is going to be 9 times 3. And the square root of 9 is 3. And then radical 3, I can't go any further. So my final answer is 3 radical 3. For the square root of 45, same idea. So 45, again, I'm looking at this list right here. These are all too big. 45 is not divisible by 36, 25, 16, but it is divisible by 9. So 45 is 9 times 5. And then the square root of 9 is going to be 3. So 3 radical 5. And then finally for the last one, same thing, square root of 12. So I'm going to look at this list. These are all too big. 12 is not divisible by 9, but it is divisible by 4. So we're going to have 4 times 3, or 2 radical 3. For the last two problems we're going to look at are going to be with variables. And so we have a to the 5th. And when we look at a to the 5th, we can do this a whole bunch of different ways, right? So the easiest way, though, is if we're doing a square root, it's like we have a little imaginary index of 2 there. So we can do this a few different ways. We can either list it all out, which takes a lot of time, so you're probably not going to really want to do that for all of them. But the idea is we're looking for groups of 2. So a to the 5th, I actually have 2 groups of 2 that can come out. So I put an a to the 2nd and 1 a that's left over. So if I do the square root of a to the 5th, I would have a squared root a. Another way to do this, which is same process but a little faster, you can see, well, what is 5 divided by 2? 2 goes into 5 2 times with a remainder of 1. So the remainder would kind of stay in that radical. So either way, you'd get the same answer, a squared root a. And then finally, for the last one, x to the 9th, square root of x to the 9th. It's really like doing 9 divided by 2. So 2 goes into 9 4 times, and there's a remainder of 1. You can also write it if you write 9 of them here. And you can see I have just 4 groups. So all 4 of these get to come out, and I have a remainder of 1. These last 2 examples are on the next page, and this is what we can do if we have to simplify a radical that has values and variables, right? So for question number 9, that's the first one we're going to look at. You can see we're working with the square root of 27, a to the 11th, b to the 7th. So we're going to break that up into the value of root 27, and then I'm going to break it up maybe with the second one with the variables, a11, b7. And so the first we're going to just look at that square root of 27, and we're going to approach it the same way as we did with the other values. So which perfect square divides into 27? And so you can see, the ones that are bigger than 27 we're not going to use. 27 is not divisible by 25, by 16. It is divisible by 9. So we're going to break it up into 9 times 3, because 9 times 3 is 27. And the square root of 27 or the square root of 9 is 3. So I have 3 radical 3. We're not quite done with the problem. We got to simplify the variables now. And so remember, it's like a little imaginary index of 2 that's there. And we're really just taking out the exponents for those variables and dividing it by 2. So 11 divided by 2. 2 goes into 11 5 times. With a remainder of 1, right? Because it's an odd number, there's going to be a remainder. 7, 2 goes into 7 3 times. It's b to the 3 with a remainder of 1. So I'll rewrite this here. And then the last part, what's outside multiplies. So we have 3a5b3. And then in the radical, what's inside the radical goes together. So 3ab. So this would be our final answer, 3a to the 5th, b to the 3rd, root 3ab. For the second one, it's basically the same exact process, right? So we're just kind of taking it a piece at a time. So we have, for number 10, the square root of 32, a7b4. So we're going to break it up into root 32 and then root a7b4. So the square root of 32, we're going to look at our perfect square list, and we're going to work up the list. So, we're not going to use ones that are bigger than 32. 32 is not divisible by 25, but it is divisible by 16. So we'll do 16 times 2 for radical 2. And then for our variables, same thing. I'm going to divide the exponents. So 2 goes into 7 3 times with a remainder of 1. And 2 goes into 4 2 times with a remainder of nothing. And so we have a cubed b squared, root a, and then we put it together. And so our final answer is 4a cubed b squared, root 2a.